Okay, so our speaker today is Andreas Bode from the University of Wuppertal, and his title, you can see there, 6 operations and holonomicity for D modules on a rigid analytic spaces. Please, Andreas, go ahead.
Thank you very much. Thank you for the invitation. Thank you for the introduction. It's a great pleasure to speak here. So this is a talk on work about D modules, so differential operators in p-adic analytic geometry, and specifically to do with D module operations in this framework. So I will begin with some kind of general background introduction. How does this theory of D modules work in kind of more classical settings with complex geometry, for example? And I will then introduce the framework of completed D-cap modules in p-adic analytic geometry. And the main focus of this talk is then about finding a suitable categorical framework, derived categorical framework, in which it is possible to define 6 D-module operations for these p-adic D modules. And finally, I'm going to discuss some finiteness conditions and how they behave with respect to these operations. So to begin with the kind of classical story, let's for now work over the complex numbers and just consider a smooth algebraic variety over C. So in this case, you can associate to X a sheaf of differential operators, and you can study D modules, quasi-coherent modules, over this sheaf of differential operators. So very explicitly, if you pick something like the affine line, so in terms of algebraic geometry, this is just the spec of a polynomial ring. And when I say differential operators on this, I just mean the thing that you think of when I say differential operators. So these are polynomial expressions in X and partial, where partial means d by dx. Okay. So all of these expressions naturally live in the endomorphism ring of the polynomial algebra, where when I write X, I really mean multiply with X. And when I write partial, I obviously mean take the corresponding derivative. So this becomes in a natural way an algebra for just composing those endomorphisms. So in this way, you obtain a ring of differential operators. This is a non-commutative Eutherian ring. Why is it non-commutative? Well, if you just check what happens if you first multiply with X and then you derive that, the Leibniz rule tells you that that's not the same as if you did it the other way around. There's an additional term here, right? If you wrote a little f everywhere, so that's the function to which you apply this operator, you see that you get this kind of commutation relation theorem. Okay, this is called the first Weil algebra. If I did the same thing in higher dimensions with more variables, you just get exactly the same kind of expression with the corresponding partial derivatives. And you can see from this that studying modules over these rings, or over these sheaves of rings, is essentially the same as studying O modules, which are equipped with a compatible action of the tangent sheaf. So there's a compatible action by, in this case, this derivative. Okay, these differential operators and the study of the corresponding D modules arise quite naturally in several places. For example, this is a very natural way to describe differential equations in a more algebraic geometric way. This is also a very common framework to discuss the representations of Lie algebras, for example, in a more geometric way, because you get this kind of vector field description of the action here. So these D modules show up in several places, And moreover, it's a very powerful framework to consider because there is a lot of structure coming with these categories of D modules. More specifically, you have three different notions of finiteness, what it might mean for a module to be kind of finitely generated or something like this, right? I could say I consider coherent D modules, so things that are locally finitely generated or locally finitely presented over this ring D, right? If we look back to our basic example of the Weil algebra here, this is literally just saying I want it to be finitely generated over this Noetherian ring. But I could also say I only consider those things that are coherent already as O modules, right? This is a much, much stronger condition. Again, in our previous example, this means it's a finitely generated module over the polynomial ring in one variable. And then there's an additional action of my derivative. Okay, much, much stronger condition. It turns out that this guy is the same as just vector bundles with interval connection, essentially by what I just told you, right? It's a coherent O module. Turns out that the D module structure forces it then to be locally free. And this action of the tangent sheaf gives you the connection. Okay, so we have two notions of coherence, and somewhere between there's a third notion of finiteness. And this is called holonomicity, or holonomic D modules. There are various ways to define these. I'm not going to give a full formal definition at this point, but let me just say that essentially holonomic modules relate to those which are coherent over O, the same way how constructible sheaves relate to local systems, locally constant sheaves, right? So there's a suitable stratification such that on each stratum you get a vector bundle with a flat connection, that kind of thing. Okay. The reason this holonomicity condition is interesting is that you can define 6 operations for D modules. There's an inverse image functor, there's a direct image functor, there's corresponding trig versions for kind of compact support, if you will. There's a tensor product, and there's a duality functor. And all of these 6 functors preserve the notion of holonomicity, right? If you apply these functors to a holonomic D module, you get a holonomic D module, at least kind of in a suitably derived sense. So you get a complex where each cohomology group is holonomic. In fact, slightly more is true. You can view this category that I wrote here, kind of holonomic D modules, as being endowed with a 6-functor formalism in this way, right? You have these 6 functors operating on it. They satisfy various axioms about how these functors get composed, how base change works. There's an adjunction formula for these different direct and inverse image functors. There's a projection formula. All these things work here. Again, kind of analogously, and not just analogously, kind of very much in parallel to how, for example, constructible sheaves work in, say, complex manifolds, or how you can work with sheaves on the étale side, for example. So this gives a very, very powerful framework in which to study D modules, because you can manipulate them in all kinds of ways, and they remain in this nice category of holonomic D modules. So one thing I should stress here, however, that it is really necessary to do all of this in a suitable category of kind of derived category of D modules. The functors that I wrote down here are not just the derived functor of something. They are more complicated compositions of such things. So for example, if I have some morphism from X to Y between smooth algebraic varieties, I can't just take as my direct image functor the sheaf theoretic direct image. The sheaf theoretic direct image would give me something that is indeed producing an OY module, but the thing I want to get out of is an OY module with an action of the tangent sheaf, right? So I need to impose some extra structure. So here, the thing that I do is that I first tensor up with a suitable bimodule, and then this carries a module structure over f inverse dy, and then I push this forward to produce a dy module.
So,
Okay?
Sorry, just to have a naive idea, if things were all affine, so this D with the arrow are these the operators on X that are Y linear, that are linear over OY.
This sounds about right, yeah. So in this, yes. So the formal definition here is slightly tricky because I needed to kind of side change these around to make it a right dx module and the left dy module. But yeah, I guess the example to keep in mind that kind of illustrates the point. If I have some closed embedding of affines, say, right, then you already have a natural action of all those tangent vectors that are parallel to your closed subvariety. So what this tensoring up will do in that case is basically just freely adjoin the normal directions so that those tangent vectors can also add. So if I were talking about right modules instead of left modules, this transfer bimodule would just be take the f upper star of dy. And here I'm just kind of changing things around a bit using side changing with a canonical bundle to turn this into a left comma right module. Okay. Yeah, again, I don't want to spend too much time on these formula. In some sense, the only point I want to make here is that these things have to live in some derived category. So what we want to do now is look not at complex algebraic varieties, but instead look at p-adic analytic varieties. And the natural question arises there, can we find a suitable derived category where we can define such 6 functors? And once we have these 6 functors, the natural second question is, what's the correct notion of holonomicity? Is it still stable under these 6 operations? Do we get a similarly nice framework? Okay, so let's briefly talk about what was kind of known before as far as D modules on p-adic analytic varieties are concerned. So here's now our new setup. Instead of the complex numbers, I'm working with some finite extension of QP. Almost everything I'm going to say will also work for more general extensions, but for now, let me just stick to that. Instead of a smooth complex variety, I take a smooth rigid analytic variety over K. And just to introduce some more notation, R is going to be my discrete evaluation ring in K, and pi is a uniformizer. So if you like, no harm is done if you just want to fix K is equal to QP, R is ZP, and my uniformizer pi is equal to my fixed prime P. So in this case, we can consider, again, a sheaf of differential operators, but here we work with a certain completion. So let me first say what this is and then explain why we consider this particular completion. So again, I did the first example just with the affine line. Let me discuss the analog here in this context. If I give you just a closed unit disk, this is kind of the basic building block of p-adic geometry, if you will. Functions on this are given by the so-called Tate algebra. So these are power series in one variable where the coefficients tend to 0. These are all the power series which converge on this disk of radius 1. And earlier, the corresponding ring of differential operators that we got was essentially looking like polynomials in 2 variables, right? It was non-commutative, but in terms of what the expressions were, it looked like polynomials in 2 variables. Or if you think about it more geometrically, this was a suitable non-commutative version of functions on the cotangent bundle. right? It was A1 times A1. So the completion, the convergence condition that we choose here, is kind of motivated by this. I again choose now power series expressions in two variables, x and partial. And the convergence condition that I impose is the one that's inspired by what things look like on the cotangent bundle. Okay. The issue here is that if I take the cotangent bundle of the closed unit disk, I don't get disk times disk, right? I get disk times some big affine line, which is non-compact. So whereas p-adic analytic geometry likes these compact closed disks, the space that I kind of think of here is something non-compact. This is why I need to write things here in terms of a limit where I let the radius in the cotangent direction, in the partial direction, go to infinity. Another way of saying this now is that this completion, d cap of x, has elements which are power series in x and partial, such that the expressions look like functions which would converge on the entire cotangent bundle of the closed unit disk. So in the x direction, I have this type of convergence condition, but in the partial direction, I have the much stronger convergence condition, namely, so to speak, the radius of convergence here is infinity. Right? If I rescale everything by pi to the n to an arbitrary integer n, then this still goes to 0, still converges. Okay? So each of these guys here is naturally a Banach algebra. So the gadget that I have here is a natural inverse limit of Banach algebra, so a Frechet algebra. This is the object that I'm concerned with. As I said, the convergence condition is kind of inspired by considering the cotangent bundle. It's also kind of natural thing that shows up if you want to have representation theoretic applications here. So what are modules over this? So Ardakov and Wadsley started studying this, and as is quite often the case in p-adic analytic geometry, it's quite hard to do things kind of with quasi-coherent modules, but there's a good theory of coherent modules. So here's the analog of what coherent modules are now. It's just the analog of what coherent modules would be on the cotangent bundle. So they are called co-admissible modules over this sheaf d cap. And well, what should co-admissible, or if you like, coherent d cap modules be? Well, they are coherent on this big non-compact thing. So on each level, on each finite radius of convergence, I give you some finitely generated dn module, and then I take the limit. And whenever I shrink the radius of convergence, the corresponding modules are just given by localization, by tensor down. So the co-admissible d cap of x module is the same as giving for each level n a finitely generated module mn, which are compatible via this tensor product rule, and then I take the limit of these. Okay, so this is what a co-admissible module over these global sections are, and then if I want to talk about the sheaf co-admissible modules, there's a suitable tensor product localization procedure to talk about co-admissible d cap of x modules. Okay, so this is where we stand at the moment. We have a sheaf of differential operators, and we can talk about co-admissible modules as kind of the analog of coherent d modules. The problem with this is that if I just have coherent stuff, I can't develop a framework of 6 functors, right? I need much more in terms of, for example, injective and projective resolutions. I need some derived category on which I define my 6 functors, and only then can I talk really about holonomicity. So I need to find a good categorical framework for this. And the first problem I run into here is that all of my guys here are naturally endowed with some kind of Frechet topology, right? These are inverse limits, again, of Banach spaces. So I need to find a good categorical framework which takes this into account and still allows for all the homological algebra that is necessary to derive my functors and so on, right? I want to have a good derived completed tensor product, for example. And then I can ask about holonomicity. And if you start looking at this, it turns out that the first basic definitions you could come up with are actually not working quite right. So this is quite subtle. Okay. Before I go on, are there any questions so far?
I have a question.
Mm-hmm.
This tensor product here, is this the algebraic tensor product, or is this also a completed tensor product?
So in this situation, it's all the same, so to speak, right? So if you have
okay,
finitely generated,
finiteness. Okay,
it's finitely generated over some Banach-Noetherian ring. So this is a canonical Banach structure, but the corresponding tensoring up is the same as the completed tensor product. So here, there's no ambiguity, and again, like up to here, you kind of can define everything completely algebraically because the topology is completely canonical in some sense. Only now, where I want to talk about and so on, it becomes important to keep the topology in mind.
Okay, thanks.
Okay.
Sorry, when you say the category of topological modules is not abelian, is it exact?
Yes. So we're going to mention this. Basically, I mean, the reason these things usually fail is that there's no isomorphism theorem, right? So something like if you have a morphism, source modulo kernel is not the same as, not homeomorphic to the image because the subspace topology is not the same as the quotient topology. You get a continuous bijection, which is not a homeomorphism. And again, like we're going to fix this precisely by looking at a suitably well-behaved exact category where derived things work out in a nice way.
Okay.
Okay, so let me briefly tell you what this categorical setting is going to be for us. It's not quite going to be topological things. I'm going to work with bornological things instead. So what are those? Well, if I gave you a topological vector space, it would be a vector space together with a collection of open subsets. Here, I'm talking about bornological vector spaces. So these are vector spaces together with a collection of bounded subsets. These need to satisfy natural axioms, which just mean kind of they behave the same way how bounded subsets should behave. So a singleton element is bounded. If I take a finite union of bounded sets, then that's still a bounded subset. If I pass to a subset of something bounded, that's bounded. And you can rescale by some scalar or take the convex hull. So take the R module generated by some bounded set, that's still a bounded set. So this is the kind of vector space that I'm going to consider here. The category I'm working with here are just bornological vector spaces. So the morphisms are k-linear maps, which send bounded subsets to bounded subsets.
So R is your complete valuation ring, and K is field of fractions.
That's correct. Yeah. Okay. So to come back to kind of the topological perspective, if you have something, say, a Banach space, or more generally something that's endowed with a family of seminorms, there's a natural way to turn this into a bornological vector space in the obvious way, right? Something is bounded if it's bounded with respect to that seminorm. So if I have a family of seminorms, I just say it's a bounded set if and only if the corresponding image in R is bounded for each seminorm. So in this way, I can take locally convex topological vector spaces and bornologify them. Okay, so there's a functor of bornologification, and there's also a left adjoint going the other way to kind of homologize things again. It turns out that if I restrict to metrizable spaces, these are actually becoming fully faithful. So on metrizable spaces, this becomes an equivalence of categories. So in particular, Banach spaces, Frechet spaces, all the things that we've seen so far can naturally be considered just as sitting inside this kind of certain complete bornological vector spaces. Why am I working with this instead of just locally convex topological vector spaces or something like this? The reason for that is that these categories have very, very nice categorical properties. In particular, the tensor product is much better behaved. So here's kind of one theorem that summarizes all the good properties for this category. This was kind of developed by Jean-Pierre Schneiders and Osman Schneiders. So if I consider complete bornological K-vector spaces, this contains Banach spaces, Frechet spaces, then this has all limits, it has all co-limits, has enough projectives, and it's a quasi-abelian category. This is a particular type of exact category where basically, if I, instead of considering arbitrary morphisms, I only consider those morphisms where the isomorphism theorem does work, then everything goes through as if my category was abelian. Okay. Moreover, this means that I can actually form a derived category of complete bornological K-vector spaces, and this turns out to be equivalent to the derived category of some abelian category called its left heart, or if you like, its abelian envelope. And this turns out to be a grothendieck abelian category, has enough injectives, so you also get injective resolutions there. I already mentioned that here the tensor product is nicer than in the topological setting. So if I start with completed tensor product of Banach spaces, then I can extend this to a completed tensor product of complete bornological vector spaces. And this turns out to give this category a structure of a closed symmetric monoidal category. So here you have a tensor homojunction, which you don't have in a topological context. All of this together means that if I give you some complete bornological K algebra, then you can make sense of the derived category of complete bornological A modules. It works in exactly the same way as if I was talking about some abelian category. You can derive functors because you have injective and projective resolutions. Everything works incredibly nicely.
I have a question.
Mm-hmm.
Is it ever possible to make this left heart explicit?
Yeah, so you can make this relatively explicit, I guess, by remembering that this is kind of going to be the category in which kind of cohomology of a complex in this derived category will take values, right? So you can represent an object in the left heart as a monomorphism in complete bornological vector spaces up to the kind of usual localization procedures that you do in derived categories. Okay? Mm-hmm. So the reason for this is basically that originally, if you take cohomology of some complex, you do kernel modulo image, right? And now, well, you don't want to take kernel modulo image because then you use lots of information, namely what was the quotient topology on source modulo kernel instead of the image that you're quotienting out by. So you can remember all of this if you instead write it out as, instead of kernel modulo image, it's a monomorphism going from source modulo kernel, so that's the co-image, embeds into the kernel. So that's kind of what your object in the left heart looks like.
Okay. Thanks.
And this also tells you then kind of, okay, the cohomology group will actually live in your quasi-abelian category precisely if the corresponding morphism is strict, i.e. if it satisfies the isomorphism theorem. Okay, so the next punchline is not surprising. The sheaf d-cap that we had earlier fits into this framework, so I can do all the things that I promised. On affinoids, I already mentioned this. The sections of d-cap form a natural Frechet algebra. So this endows the entire sheaf with the structure of a sheaf of complete bornological K-algebras. In the same way, if I have a co-admissible module, this is locally given by Frechet spaces, so this is a complete bornological module. In fact, you can make a bornologification functor here, which sends a co-admissible module to a corresponding complete bornological module, and this functor is both exact and fully faithful. So the previous theory of kind of coherent modules that Ardakov-Wadsley developed really fits inside this framework as a full subcategory. And moreover, as I said in the slide before, this is now a framework in which I can talk about derived categories and derived functors. So I can now basically just write down analogues of the 6 functors in strict analogy to how things work in the complex algebraic world. Right? The direct image is now exactly the same thing as before, except that everywhere that I encounter something, I just put little completion symbols on top, right? I could have written this down already on the third slide or something. The point is now that I have made sense of what this means. This completed derived tensor product is perfectly well behaved now as a functor on this derived category of complete bornological modules. Then again, okay, this is kind of completed version of the earlier transfer Y module. And then this functor behaves exactly as before in some sense. So what we've done now essentially is, instead of looking at just co-admissible modules, we look at a really, really big category of all complete bornological decap modules. This is really, really large to allow the formation of these 6 functors. The downside of this is that this category is so ridiculously large that you can never hope for a good behavior of these functors on the entire thing, right? Note, for example, that so far I have not imposed any kind of quasi-coherence condition or anything, right? These are literally just sheaves of modules, nothing further. So it's a really, really big category, lots of crazy behavior. So what we should do now is look at suitable subcategories of my derived category, which incorporate suitable finiteness conditions, and see how do these 6 functors, direct and inverse image, tensor product, duality, how do they behave with respect to these finiteness conditions, right? Ideally, what I would like to have is a notion of holonomic decap module, which is just stable under all these 6 functors, and ideally gives me some kind of 6 functor formalism there, in the same way as in the earlier complex algebraic setting, right? So let's begin with something that is slightly easier, namely, let's take the analog of this category here, bounded coherent. We already know what the analog of coherent is. It's just co-admissible. So I now just take the corresponding derived version of this, if you will. So if you have any smooth aphenoid, think back to the closed unit disk that I gave as the basic example. Then on that aphenoid, you can describe the sheaf decap as an inverse limit of suitable Noetherian-Banach sheaves. By which I mean, if you choose some aphenoid and you look at what the sections are there, they're going to be an inverse limit of Noetherian-Banach algebras, right? In the example that I gave, where we had this kind of inverse limit of kx pi to the n partial, I'm talking about these dn's, kx pi to the n partial. And something is co-admissible if and only if it becomes coherent over dn under base change, and it's the inverse limit of such guys. Right? This is, in some sense, the complete bornological reformulation of what it means for something to be co-admissible. But again, it follows the same philosophy, right? It's just the inverse limit of things that are coherent on the Noetherian level for any finite radius of convergence. The reason I put down this lemma is that if you write things like this, it becomes much easier to guess what the corresponding derived version should be, right? If I take some complex of complete bornological D-modules, then I'm going to say that it's a C complex or co-admissible complex if the base change to the finite level always gives me something bounded coherent, and I need to find some suitable analog of this inverse limit condition. So let me here just work kind of on the cohomology groups and say for each cohomology group, Hj of M is giving us the inverse limit of the corresponding coherent guys here.
So, sorry, when you say cohomology group, I mean, you mean the groups we all know and love, or you mean objects of this heart or whatever?
Very good question. So a priori, these things would be objects of the left heart, because that's how this game works, so to speak, right? You take a complex of complete bornological things, then the cohomology in each degree is something in the left heart. However, my original category, complete bornological things, lives inside this left heart, right? Because I said earlier, you can describe the left heart, objects in the left heart are kind of monomorphisms, and up to some kind of inversion. And the complete bornological guys, and there are precisely those monomorphisms which are just 0 goes into something, okay? And it turns out that all the things that I'm interested in here will actually have cohomology groups that are kind of strict, so that already live in the complete bornological world rather than in the big left heart. Does it make sense?
Yeah, but I mean, if you have a complex of sheaves, you can take cohomology that gives you a sheaf, or you can take take global section, something. So here, when you say
so
group,
this is really cohomology in a degree. So you get an object which is in the left part of complete bornological sheaves, which turns out to be the same as sheaves of, or sheaves with values in the left heart.
Mm-hmm.
Okay.
Which happens to be sheaves with values in these complete bornological modules.
Yeah, exactly. Yeah. So yeah, there are some slight categorical subtleties here. I mean, already said that the left heart of the sheaf category is the same as sheaves with values in the left heart. So there are various kind of tricks to play here to make this work. But essentially, once this is kind of set up properly, all these subtleties go away, because as I said, once you do this, for all the well-behaved complexes like this, it turns out that the cohomology is really a sheaf of complete bornological vector spaces. No left heart anymore. Everything is strict. Everything works well. Okay. So this is kind of the analog of bounded coherent things. And it's not hard to see from the definition, if you pour in some functional analysis, that the cohomology groups that you get here are indeed co-admissible modules, right? They're given as the inverse limit of some suitable coherent guys on level n. And in fact, this is basically an if and only if. So if I have some bounded complex, then being a C complex is really the same as saying all the cohomology groups are co-admissible modules. Okay. Moreover, this notion of C complex really behaves under my 6 operations the same way how bounded coherent C modules would behave in the classical story. So here's a summary of the stability properties that you can expect for kind of coherent stuff. If I have a smooth morphism, then the inverse image will preserve C complexes. If I have a projective morphism, then the direct image will preserve C complexes. The duality functor preserves C complexes, and it is really a duality functor in the sense that if I do it twice, I get the original C complex back. Moreover, this duality thing that is really kind of defined to be essentially R hom into dx in the complete bornological world turns out to be the same as if you did this algebraically. So this computes standard X modules, if you like. You notice that here, when I'm working with C complexes, or if you prefer coherent modules, I need to impose lots of extra conditions to make this work, right? This is the same if you do things in complex algebraic geometry. The notion of coherence will only be preserved under lots of extra conditions, right? This is not surprising. If you look at my big ring of differential operators and you pull it back to a point, that's not going to be a finite dimensional vector space. But yeah, if you have these extra conditions, then it works. For a more general framework, we're going to talk about holonomicity in a second.
So the traditional definition of a holonomic modulo of V, doesn't it have to do with some duality?
Yes, this is an excellent question. So let me list a couple of equivalent definitions of what it would mean to be holonomic for complex algebraic D-modules. First of all, now that I have a duality functor, I can say a coherent D-module is holonomic if and only if its dual is concentrated in degree 0. So in terms of this interpretation, that means all the X groups vanish except for one. There's a shift here that I'm sweeping under the carpet, so it's actually the X group in degree dimension of the space. But this is kind of one way to define this. All smaller X groups vanish. And in fact, this was the first thing that we considered also in this p-adic analytic context. So there's a paper by Konstantin Ardakov, Simon Wadsley, and myself, which discusses what we call weakly holonomic decap modules, which are precisely co-admissible decap modules which satisfy that property. The problem with that is that it turns out that this property is really not so well behaved. There's many difficulties here that are basically all encapsulated in the fact that I have this limit, this inverse limit of Noetherian guys. In some sense, defining this in terms of the dual is the same as requiring a certain niceness property on each Noetherian level without properly controlling what happens in the limit. We can discuss this later on a bit more in detail. But yeah, so this is one thing you can do. It's not the road I'm going to take precisely because this would give me something that's ill-behaved. There's another definition that's closely related to this that has to do with the dimension of the associated singular support, the associated characteristic variety of a module. And that's basically the same thing, except that in this setting, we can't define at the moment what a characteristic variety, what a support of these things would be. So this approach I'm also not going to take because we don't know how to do it. I'm going to take a very formal categorical approach to do this. Let me first mention another result that's kind of in strict analogy to other contexts of D modules. So the direct image that I've defined can also be used to compute the RAM cohomology. Whenever I take the direct image of the structure sheaf along the structural morphism, so just down to a point, then this essentially computes the RAM cohomology. This has just to do with picking a suitable free resolution of O as a D module. This gives you some kind of Koszul resolution, which basically produces the RAM complex shifted in degree. So this is where this is coming from. Note, however, that this is highly problematic, right? Because in p-adic rigid analytic geometry, the RAM cohomology can be incredibly ill-behaved. If you just pick the closed unit disk as an example, it has really, really nasty RAM cohomology. So this tells you right away, even if I pick something as nice as the structure sheaf, a really, really nice decap module, if I apply my direct image functor to it, I get something that's horrible. So this tells us immediately that this direct image can, in principle, be really problematic, right? In the complex algebraic situations, you know that whatever it is, it has to be a holonomic D module on a point, which is a convoluted way of saying it has finite dimensional cohomology in each degree. Okay? Finite over a point. And this is no longer true here. So in particular, you know that this direct image here turns out to be no longer a C-complex. So here there are instances where you can take a nice module, you apply direct image, and it takes you out of the finiteness condition. It's very problematic. I'm going to come back to this in a second. Let me now define what a holonomic DCAT module should be. And here I'm going to follow an approach introduced by Daniel Caro for kind of D modules in positive characteristic, which basically just feeds all the desired stability properties into the definition and then shows that this is a suitable category. So lots of text. What this is saying is a C-complex is holonomic if it is a C-complex which stays a C-complex under any finite succession of the duality functor, the inverse image functor, and taking local cohomology in some divisor. Okay, so an inductive way of writing this down is it's a C-complex which stays a C-complex under inverse image and local cohomology. And then it's n holonomic if it has this property in n-1 steps, plus it stays n-1 holonomic if all of these duals remain n-1 holonomic. Okay,
so being a C-complex would be like a -1 holonomicity.
Pardon? Oh, you're muted.
Being a C-complex would be like a -1 degree of holonomicity.
Yes, yeah, that's absolutely right. Yeah. So this is what Caro did in his setting to define a six-functor formalism there. So we're just going to do the same thing. And notice that basically half of the stability properties are already present here. I get for free that this notion of holonomicity is stable under smooth inverse image, local cohomology, and duality operations. So this I already got for free. It turns out that a very large part of the rest I basically get just through diagram chases and using base change arguments. So at this point, there is no functional analysis whatsoever. Things become very categorical, very formal. So let me start with the bottom theorem. This notion of holonomicity is indeed stable under the inverse image operations, the duality operation. This is trivial because it's part of the definition in some sense. And you also get stability under the direct image operations, at least whenever the morphism is protected, right? I already knew from 2 slides ago that I can't get this for an arbitrary f because I gave you this de Rham cohomology counterexample. But at least when f is protective, you can do a diagram chase argument that this is fine. And moreover, you get, as promised, base change formula, projection formula. You have these adjunctions between direct images and inverse images. So all of this is fine. I guess the other thing that we now need to convince ourselves of is that this wonderful definition of holonomicity contains more than just 0, right? The way I set this up, this could be a very stupid, boring category. So I need to make sure that all the things that I would kind of classically expect to be holonomic are actually holonomic. So this is where the top theorem comes in. If you consider DCAT modules that are already coherent over O, so these are the vector bundles with flat or integrable connection that I mentioned in the very beginning, kind of the strictest finiteness condition. All of these are holonomic in the sense that I said in the previous slide. The tricky bit here is basically showing that local cohomology is fine. And this is what we already did in 2020. And then you can bootstrap from there. So this shows that it's 0 holonomic, and then you run some additional excision sequences and diagram chases to show that it is n holonomic for every n. So you get all of these things in there. So the category of holonomic D modules is not just some stupid, almost empty thing, and it has all of these nice stability properties.
So in the picture you put at the very beginning, you said, well, here are decoherent modules. Here are those T modules which are co-coherent, and holonomic modules are in the middle. Now, what you're saying is that the very bottom is containing what you have. Now, you need to show that there are more, right?
So, yeah, instead of coherent here, these would now be co-admissible or C complexes. And then I have coherent over O is indeed contained in holonomic, is by definition contained in C complexes. So I get the same set of inclusions as before. Of course, you also get lots of holonomic things that are not vector bundles with integral connection, because you can now apply the functors for which you have stability properties. So I could start with the structure sheaf and then say restrict it to some Zariski open and push it forward again. That's also going to be a holonomic decap module because it fits into an excision sequence with local cohomology. And then, yeah, so in this way, you can produce more examples that are not just coherent over O, but still sit in this middle category.
But I mean, you did say that if you took direct image of the structure sheet, you got out of the category.
Yes. So
yeah.
In general, holonomicity is not going to be stable under arbitrary direct image, but it is going to work whenever F is projective. I think proper is also fine, but I haven't proved that yet.
Okay.
So this is the one bit where the theory really diverges, and this has to do with kind of slightly subtle p-adic boundary behavior, if you will. So there's one possible improvement where instead of doing things this way, you kind of have some over-convergent Decker structure, right? This would get rid of the earlier example with the Durham cohomology, because then you get finite dimensional Durham cohomology. But even that isn't enough to correct for everything. If you have examples like you embed one disk into a slightly larger disk, this will never work however you correct it. So there will always be some kind of modifications required for these direct images. The other thing that you might notice here is that at the moment I write down 5 functors, right? There's the 2 inverse images, there are 2 direct images which happen to agree anyway on the projective bit, and there's a duality functor. I haven't said anything about tensor product. Tensor product is the subtle one, which was also the most difficult one for Caro. And basically the hope is that that you can also prove stability on a tensor product, but this is going to be quite subtle. The idea should be, philosophically, holonomic decap modules should be kind of constructible out of integrable connections. And then you run a descent argument. That if I take 2 vector bundles and tensor them together, that's a vector bundle. Now, if your things look like that on each stratification, hopefully you can build this together in a sensible way. That's kind of the idea. But making this precise from this very formal definition that I gave you, that's quite tricky. So that's kind of the 6th functor that's still missing at the moment. Okay, so pardon?
So it's the 5 functor formalism.
Yes, that's why I'm very careful to name my talks 6 operations for decap modules, rather than saying here's a 6 functor formalism, right? Because I define 6 operations, but so far I only tell you that 5 of them are well behaved. Yeah. Okay. So yeah, you can guess now what's still missing. Like it would be very nice to also say tensor product works well. Similarly, there are some additional statements that have to do with this kind of constructibility idea. If I had something like holonomic decap modules are those that are constructible in a suitable sense, that would be really powerful to say something about finite length results for these modules, which then in turn would be very useful both for applications in p-adic differential equations and for doing things in p-adic representation theory that I haven't talked about at all in this talk, but there's lots of interesting things going on here to use these objects in order to understand p-adic representations. And so having this toolbox of operations and knowing that they preserve certain finiteness conditions is really useful from that viewpoint as well. And I think I'm just going to stop here. Thank you very much.
Okay, thank you very much for your very nice talk. Are there any questions from the audience?
I have one. So in, let's say, the condensed framework, there is another notion of finiteness, which is what, I mean, this sort of story seems to be about, which uses nuclearity. Now, you can also take nuclear modules over your D of X, and then take the derived category of that. Do you know if your functors are well behaved on this category?
So here's what I can tell you. This is still work in progress together with Simon Wadsley and Finn Wirsig, who's a PhD student of Konstantin Ardakov. This category of C complexes that we have here is basically, if you write things down actually in an infinity categorical language, this is just gluing these bounded coherent guys together. Okay, so this is really saying if you have something coherent, it means you have something coherent on each level and they fit together compatibly. And you can do this in this framework as a kind of whole subcategory of things of complete bornological nature. You can do exactly the same thing in this condensed framework. So these guys here also embed fully faithfully into a suitable category of condensed D-cap of X modules. All the functors that are relevant in the definition of holonomicity then get translated compatibly. So you can make sense of C complexes in the condensed world. You can make sense of the same notion of holonomicity, and they're kind of compatible. My impression is that as soon as you leave C complexes, the theory is probably going to be much wilder in my complete bornological world, right? Because I don't have any further restrictions. So all kinds of things can happen there. But because this is designed to remain within the C complex framework, there it kind of gives you the same answers. So you get an equivalent theory.
Yeah, but there is also, I mean, I guess my question is more along the lines of comparing the sizes of your category of C complexes and the category of nuclear modules over D of X.
Right. So, I mean, you can correct me. I was always under the impression that nuclearity in some sense is much weaker than just saying something like coherence, so to speak, right? This is more setting things up in such a way that you can talk about quasi-coherent things.
Right.
My guess would be that nuclear guy is much larger, but contains this one. Yeah.
Okay.
I have a question. I mean, when the derived complex showed up, like, you said, I mean, in your context, that was bad news that this appeared. Is this, what kind of derived complex is that? I mean, is it the dagger type?
This is a good point. So this is,
or is it p-adically complete form? So
there's no dagger here. This is kind of, if you will, the algebraic derived complex. So for the closed unit disk, this really looks like Tate algebra goes to Tate algebra times dx.
Yeah, so this is the bad one.
Yeah. So this is the really bad one.
Yeah. Okay.
Yeah.
Where kind of the H1 is infinite dimensional with lots of problems because you can't integrate arbitrary power series with some convergence conditions. So
Okay.
this is precisely saying why this guy is so badly behaved in general.
So your notion, I mean your notion of pathological is the same as mine, or it's some.
Yeah.
Yeah. So it's pathological by the same reason I consider it pathological. Okay. And the other question, which is, I mean, maybe too far-fetched, but because I think this is, I mean, the singular case, the case of singular schemes is problematic even in the complex analytic case. But I mean, in this, so my question is very naive, but sometimes when you want to say extend Monsky-Vasnitsa cohomology to non-smooth things, you embed it into smooth thing and then do some tune construction. So is that kind of construction of any use in this context if one wants to consider singular things?
Yes. So let me at least say that this approach in general does work here. So in the same way as for, say, algebraic d-modules over the complex numbers, there's an equivalence that tells you that if you have a closed embedding, then d-modules on the big ambient space, which are supported on your closed subvariety, is the same as if you have d-modules on the closed subvariety. So you can kind of use this to get a well-defined notion of what a d-module on a singular variety is. There's also there's a very technical alternative to this that maybe goes more kind of in the direction of more sophisticated derived analysis. You can always view, or the category of D modules is also equivalent to a category of O modules on an associated RAM stack. And this, in principle, makes sense in like very, very, very large generality if you are willing to define such size. So this is currently work in progress by Juan Esteban Rodriguez Camargo, who's kind of taking this condensed approach to define the RAM stacks in p-adic analytic geometry. And the hope is that this kind of links up with our theory of D modules, but that's not confirmed yet.
Let's see. Okay, so are there any other questions? If not, I'll stop the recording now.